Hello, everybody. As I promised yesterday in my last video, I want to continue talking about machine learning. In that video, and I have the notes that went with it, they've already been posted. I was talking about a network that could learn to classify items for us. The basic form was just two inputs and an output, but we can put hidden layers between the two. And this was the form I had shown at the end. Now I'm going to, working from a website, and I will show you the website in a few minutes. I'm going to try to talk about some of the more interesting mathematics that is necessary to do this. So let's go to this and talk through these things here. Let's suppose we have this network. If you'll notice now, there's a separate weight on each arc and there's separate biases for each of the nodes. So, for example, the output at H0 equals, I have that further down here, H0 equals 1 over 1 plus e to the minus y. That is the sigmoid function, which is the function we're using to smooth things out, where y equals multiply W0 by L1, L0, multiply W3 times L1, add them together, and add the bias, and then that's the y that we put in to the sigmoid function. We do the same thing at H1, and we do it also at O. So O0 is 1 plus the e to the minus x, where again, we compute x by doing the arithmetic W4 times whatever H0 is, plus W5 times whatever H1 is, plus the bias B2. I should have wrote B2 there. That's okay. Now, that gives us the output. How do we train this network so it will be able to discover the right answer? Well, that involves building up a set of training data. We need a set of known cases, whatever those known cases are. And what we do is we input a set of samples where each of the example consists of the characteristics of whatever we're working with and our determination of what the answer should be. I'm generalizing this. We input the initial weights and the biases, and then we go to work training our network. How do we train it? We do the arithmetic to compute the output for each case. Now I have this in Python over here for the case I'm going to be talking about. Here's the input. We have 4 people that we know, 2 females, 2 males. We know that when we did the rearranging of the weights and the heights, these were the inputs at L0 and L1. So for Alice, it was -2, -1. For Bob, it was 25 and 6. These were the answers. 1 represented a female and 0 represented a male. So we're giving the machine an array of the characteristics that it's getting in, its inputs, and we're giving the program an array of the correct answers. Now, that's the input we have to have. Then up here, if you look way up here, as we did before, we defined the sigmoid. And now we're going to define something called the derivative of the sigmoid, which I'll talk about in a few minutes. And we have to figure out, how do we determine how good the computer did, how well it did. In what I talked about last time, this was the measure of how good or bad the result is. The method that most of people use is called the mean square method. And it's very easy. It says, take the true ones, the correct results, subtract, take the results that you're getting, minus what you think they should be, and square it so that you don't end up having to have negatives. And then you're going to divide by the mean, divide by the average. That dot mean means take the average. So it's really sum up all the differences between what you got and what you should have got, squaring the differences so you don't have to have negatives, and then dividing by however many cases you have to get the average. So that's a pretty common way to determine how good things are. It's used when you're trying to get a set of data and you're graphing it and you're trying to find the best line that fits it. It's the same way. You compute where you are minus where it isn't, where the line says it should be, and do all this work and get the mean square again. So that's the method we will use to figure out the loss. So now we have expanded this. We can decide how well we want to do, how close we want to get. Then the question becomes, how in the world do you improve the guessing? How do you make it better? You can't just go at random. There are lots of possible numbers for the weights and the biases. We can't just pick them out of midair. We do to start with. In fact, the computer had it, will do it by random. It'll just take some things from the set of possibilities. But once we get a set of answers, we want to do the whole thing again. But this time we want to use different weights and biases in the hopes that we will improve the answer. So how do we go in the right direction? Well, this involves calculus. It involves the gradient, and it involves partial derivatives. So to remind you of the world of calculus, which I think most of you are a little bit away from, here's what we're going to do. The loss is the sum of the predicted value minus the actual value, and it's actually for each of the, actually it's square that. We should be squaring these, and then we should be dividing by the number of cases. I've defined the function that we're going to be using. That's the function that smooths it out, and that's just 1 over 1 plus e to the minus t. This is called the sigmoid function, which I've mentioned before, and its output has to be between 0 and 1. Now, the books seem to say it is in the open interval between 0 and 1, which would mean it cannot assume 0 and 1 as answers. But some of the computations I've done show it assuming 1. The loss, let's look at order O0, the output. Again, the way we get the output is to compute the values coming in it and put it through the sigmoid. So 1 over 1 plus e to the minus x, where x is whatever comes in from this computation. Well, we get x by taking W4 times H0 plus W5 times H1 plus the bias B2. Well, so far so good. But now, where do we get the H0 and the H1? Well, the H0 is done the same way. It's 1 over 1 plus e to the minus y, where y is W0 times L0 plus W3 times L1 plus B0. And the same way here, where I think I used, well, I should have used Z, but we'll see, where you have Z equal W1 times L1 plus W2 times L0. I think I have to be careful of this. It's W1 times L1, pardon me, and W2 times L0. Now, what we do is we pick a case. And our goal, the mathematics says that if you want to get closer to the answer, you have to compute the partial derivative and move in that direction that the partial derivative tells you to move in. So we need the partial derivative of the loss function with respect to each of the weights. So weight 0, for example. How does the loss function depend on weight 0? What happens when you change weight 0 and hold everything else together the same? That's what a partial function is, a partial derivative is. It tells you what that change will be. So we need to compute the partial of the loss with respect to W0. But that's not as easy as it sounds. What we're going to do is we're going to use the chain rule. The chain rule says you can start with the partial of the loss, basically partial x over partial y equals partial x over partial z times partial z over partial y. It just keeps chaining them together. And that's what we're going to do. We're going to get the loss for H0, and that will give us, that we get from the loss over the actual times the change in the actual based on H0. And the actual based on H0, W0, which is what I want, is the actual based on H0 times the change in H0 over W0. So we play around with it. We have this formula, and we know how to take the derivative. The derivative is the derivative of the function times the derivative of what's inside the function, where H0 is the only thing that can change. So it's W4, and everything else is a constant, and the derivative of it is 0. And the same way we keep going, and we eventually come out to the answer. Now, one thing you should know is that there's a nice definition of the derivative of the sigmoid. You can see it right here. Go down some. I think it's further down here, way down here. Here it is. The derivative of the sigmoid is e to the minus x over 1 plus e to the minus x squared. Now, how did they get that? Well, it's the derivative of a quotient. And the quotient rule says it's the denominator times the derivative of the numerator. Numerator's derivative is 0 in this case, minus the numerator, e to the minus x, times the derivative of the denominator, which is e to the minus x times minus e to the minus x. And the two minuses cancel out, so you get e to the minus x in the numerator. And everything is divided by the denominator squared. So if you remember the quotient rule, that's how it's done. Now, we have everything we need to compute the derivative, the partial. What we do is we take the partial derivative in one case. You pick any case, and you do the arithmetic for that case. The reason you pick one case is you have the actual output there. So where actual appears in any of these formulas, you have the number, or probably the predictor. You have what should be the answer. So you can substitute it in, and everything will come out numbers. And then when you do that, you're going to change that particular weight by that much, whatever that happens to be. And you're going to do that for every single weight and every single bias. Now, it gets even a little worse because there's another quirk in it. It's been shown that you have to be careful of how fast or how slow you do these changes. So there's another parameter called the learning rate. And in the changes, you multiply the amount that you have computed you should change by the learning rate to get the actual amount you're going to change. Now, all of this is a lot of arithmetic. It's not very, very difficult if you can remember your calculus. It's one of the nicer applications of calculus, especially partial derivatives. And you can see that people who are involved in machine learning better know a lot about the calculus to be able to do some of these. What it works really nicely for our sake is that this website has a complete program to solve this problem. So I put it in my Python and I ran it. And this is the answers I got. You'll notice that the female side, I was getting answers like 0.95. And for the male side, I'm getting answers like 0.039. And remember, we said 1 would be for the female, and 0 would be for the male. So we're getting pretty good answers. Now, you see something called epoch there. What an epoch is how many times you're going to go through this. Each time you go through the corrections and recomputing, that's a new epoch. And you can decide how many epochs you're going to go through. That's the way they really do it instead of checking on the difference, whether the difference is acceptable or not. You can look at this program. It's on the website. And again, after you do all the definitions of what you need here, and there's the definition of the loss, you have to build in what you need. There is the way they pick the random numbers, the weights. They make them totally random based on the normal distribution. And they do the same thing for the biases. Then we compute the actual H1s and H2s. Self W.W1 times X0 plus self .X W2 times X1 plus self .B1. And we do that. We compute O1 and we return O1, which is the answer. Now, to train it, the learning rate's going to be 0.1. We're going to have 1,000 trials. For each trial, we bring in the data we have. The data is going to be the characteristics and the answer. Now, that zip may mean they were reading it from a file, but whatever happened, it's in here anyway, so even if it comes in from a file, it doesn't matter. And here are the work involved in computing everything in sight. You can see those are the partials. It's hard to write partial in a computer program. And there's a lot of it, but it's all straightforward. Here's the changes of the various parameters, the weights. The changes continue. There were 9 parameters. Here's an output. I added this portion right here because I wanted to watch it actually output. There was no output. It was just showing the error, the loss. I wanted to see how well it was doing. So I printed out the actual computations that the machine made, what its answers were. And then here's the data that we need to put in. We have the array, that is the values of the inputs, the array, that is the values of the output. Notice for the input, there are 2 parameters, so they have to be, for each case, they have to be a list also. They can't just go in separately. And then we have the actual calling of everything, and that's it. Now this program is a little, is what might be called a toy program. It isn't hasn't got all the bells and whistles you would get from a fully operational machine learning program, but it should give you the idea of how this works. Again, I think the most amazing part is, even right now, after running the program, I don't know what the weights are. I'd have to write them out at the end to find out what they really are. All I know is that it's doing pretty well. It's getting answers that would definitely tell me that it went to either the male or the female side. So that's what I wanted to say. Now, I have another set of data that I would like to try. I'm going to work it out to see how it will work. I don't know exactly how it's going to work. It could have more than 1 input or 2 inputs. There's a SPAM database that I got from a resource that's at the University of California, Irvine, which has lots of cases. I think I can bring it up. Give me a second. Let me see. Now, when you know it, something's in the way up there and I can't get to it. Well, I'll show it to you next time. I've been playing with it, and it's not as easy as you might think. There are a lot of little things we have to do. So I'm going to see if I can show that to you as an example or give you parts of it to do as a homework. We'll see what happens. But right now, that's it for today. I hope you made it through the weekend. It was so beautiful out. It was amazing. And I'll hope to see you sometime soon. Bye now.